I get to my studio thing. So, just want to remind everybody that this playlist on YouTube does exist, right? I'm noticing my view counts before a lecture are not probably everybody that's here. So you can indeed watch these videos beforehand. And I really feel like in some cases, I know that they're kind of complementary. But for instance, today, this is like one of the things where I'm just not going to talk about vector norms. I'm just going to assume you know what I mean when I say L1 and L2, okay? So I do want to encourage people to watch these before you come to class. All right, let me make this a little bit bigger. This is where we stopped, right? So everybody has already kind of figured out that this is this uniform interface scikit-learn. All the estimators, all the classifiers, all the regressors, they all have this fit. They all have either a predict or a transform or something like that, depending upon what kind of an object they are. And when you use them, you get, in the end, this populated object that has coefficients or weights set. It has its history, like it generally saves the data it was fit with inside the object. So when you have a fit classifier, you can see what it was fit with, usually. There's all kinds of fun things. Let me also point you out that the docs in scikit, like when somebody's asking me, how should I make the docs on my computer, my programming project, right? Like I'm creating some sort of package. Scikit-learn has by far the best documentation of any complicated software package I've ever used. So just as a general thing, right? Like how does this look? When you go to use a scikit-learn doc for a particular function, you get the usual kind of API description. It tells you exactly what something does. Okay? It has lots of stuff that are optional things that you'll have to explore to learn. It tells you what happens as usual after you fit something. You get this coefficient, variable fit, all kinds of things. Now, this is where it gets good. Usually, right afterwards, there's a little example. How to use it. Ooh, this is awesome. I love this feature. Hide prompts. Copy. Paste. Okay, just saying. It shows you like links to all the methods and what's going on. You will generally get some pretty good stuff here if you do see alsos. These are related kinds of regression, ones that we will be exploring today in the slides. Ridge regression, lasso, and the elastic net. Okay, another thing, examples that use this particular function. These are generally bigger things, right? Like you know, whatever. Quantile regression. Quantile regression is where in regular OLS, if you have proper zero mean residuals, it's fitting the mean, right? It's fitting the mean of the residuals. What if your distributions on your residuals is not Gaussian? So if you remember your statistics when you're dealing with non-parametric, non-Gaussian things, instead of means, you usually fit a median. A median is a 50th percentile. You don't even have to stop there. You can regress the 25th percentile if that's of interest to you, or the 75th percentile. That's what quantile regression is, okay? So at any rate, when you look and you click on these examples, you'll see these are like way bigger. They like show you using them in a context that you might be interested in. Okay? So these docs are supreme. And in general, like, you know, when you get to like a topic, there's also, besides the examples, there's usually something, oh, here, linear models. Like, this is halfway to a textbook, okay? Like, if you don't like my treatment of OLS, here you go, okay? So just note that this documentation is something that has been developed over about 15 years by literally hundreds of people participating. So, and it's also in multiple languages, FYI. So definitely, like, I know people who taught themselves machine learning from the documentation of scikit-learn. It is a good resource. Okay, let's follow up with what's going on here. So I got you to think about the docs. I got you to do fit and predict. Let's talk about what this plot actually shows. So 10 data points in blue, a truth in green, and the thing we fit in red. So what's a zeroth order model? Oh, sorry, is that a question?
I remember from last time the green line was like a generating function.
Yep.
What does that kind of mean?
So this toy data, those blue dots, they are random noisy versions of that green line. So there is a true relationship covered up with noise. So those blue dots, if I didn't put noise in them, they would lie straight on the green line. Does that make sense? Yeah. So every single time we draw a sample, like a training set, it's corrupted by noise. The idea of all statistical learning is there's some true deterministic relationship, that green line, corrupted by noise. This is fundamental. So definitely keep that in your head anytime we're doing machine learning, because that's the framework, right? And that's exactly how we get overfitting, which is what we're going to talk about today. Because sometimes that noise, the position of those blue dots vertically, that's random. I mean, there's some truth there, but there's some randomness too. And overfitting is when we fit those blue dots perfectly. So let's talk about this, right? Zeroth order model. A zeroth order model means we're fitting just a constant, right? So that's why it's a horizontal line. What is that constant? Yeah. It's the mean y value of those blue dots. You got it. That's exactly right. The mean y value of the blue dots is what the constant is going to fit. Okay, first order model, x plus a constant. We know what that is, that's a line. A third order model is a cubic, right? We're going to x to the cube, some parameter x cubed, some other parameter x squared, some other parameter x, and a constant. And that's how we can get this curvy nature here. Now, the thing that you may remember from algebra class is if you have 10 data points, that is 10 equations, right? And you have 10 unknowns, then you are 100% fully specified, right? There's one and only one answer, and it turns out that you can not just do that, you can hit every single data point straight on. There is zero training set error with a ninth order polynomial, right? So it turns out it actually happens not at 10, but at ninth order, because you lose a degree of freedom just immediately with the fact that you have a constant in there, okay? So x to the ninth power, you actually have 10 coefficients, right? Because you have that constant. So what do we think? Is any one of these overfit, and why? Pretty clearly overfit. Why is it overfit?
Because theoretically, if you were to apply that function to points, it wouldn't hit them because it's fitted to the training data.
Yeah. So for instance, see if this works. If I draw a brand new data set, which is that true green line plus new noise, and noise is random every time, I'll get, I should thank Gwen for leaving me blue chalk, right? And that line, that red line is going to stay the same with that new data set, right? The red line was fit on my training data. This is like test data, right? Ain't nowhere near. I'm perfectly fit to my training data, which means perfectly fit to the noise in that training data. Okay, so absolutely, when we're in a situation, I'm probably in trouble, aren't I? Those aren't going away. Oh well. So we're probably in a situation where when we have the same number order as the number of data points, we're clearly overfit. But even if I went like probably between third order and ninth order, you might make an argument for being overfit on the data. Where am I clearly underfit on the data? Yeah. Yeah, and why is that? Yeah. So there's the eyeball test, right? Which is that even if we didn't see that green line, it certainly seems like there's something more than a constant there, right? So bare minimum, we've got the eyeball test. And that's not sucky, right? The eyeball test ain't nothing. If you can squint at it and you can say, yeah, I can pretty much see that kind of a model is a decent model, at the very least, your squinting at it is going to accurately say, this is crap, this is crap. Those are good intuitions. There's nothing wrong with that. But there's maybe it's harder to pick between first and third order. So we want to think about how to actually do that in a quantitative way, right? Not just the eyeball test. So we're going to talk a little bit about that for sure. Okay, let me leave you with one more thing. This data set is super toy, right? I just want to remind you, I did give you some options here if you want to play around. If you want to try other toy data, all you've got to do is take func and assign it to a polynomial function or a sinusoidal function. You can try other stuff with this notebook. But let me show you, there does exist in scikit data sets that you can load up. So the Linerud data set has got some data from middle-aged men in a health club. And it's measurements of how many chin-ups, sit-ups, jump-ups, or whatever that is they can do, and measurements of waist, weight, pulse rate, resting pulse, right? So this is a regression data set. It's at least slightly more interesting than the toy. You could, load it up, get x's and y's. Okay? How would we fit it? Anybody want to yell out at me? Come on. I know it's after lunch, but what do I type?
Is it X train, Y train?
Yep. Okay. So we need to make a training set. Oh, we have all the x's and all the y's. That would be all of our data. Can we make a training set? Train, test, split. How does this work? I am super lazy. I'm just going to copy stuff. Lost my thing. Is that it? That's it. Okay. So if we did this, we'd be fitting on all of our data. We wouldn't have a good estimate of whether we were overfit to the noise. So let's get ourselves a training data set and a test data set. Just to note that I call them X's and Y's. So that's our inputs. I think you can figure out the testing set size is going to be 1/3 of the data. 2/3 of the data will go to training. 1/3 will go to testing. Now, you may or may not realize this, but since we have a fixed data set, if we randomly assign data points to training set, that's our ideal, right? We don't want to just take the first 2/3 because oftentimes data sets come ordered, right? Like maybe the data set is got time in it. So the first guy that got measured came in at 5:30 in the morning. And the last guy that got measured came in at 12:30 in the morning. What if early people are way fitter than late people? I don't know. I'm just making stuff up, right? The point is that your data could have confounds in it, especially if there's temporal ordering in the original data set. So you always want to randomly permute the data before you throw it into training set and test set, just to get rid of potential confounds like that. Now, let me be blunt. That's the minimum you should do. There may be even crazier things you're going to have to take care of. Weird confounds that relate to batching or grouping of data. Okay? We're going to talk about this throughout the quarter. We're going to refine our ideas of how we create good splits. But I just want to give you the concept that you probably want to start there at least. Okay. So that's why we have our random state here. Who's our CS guru who's going to explain random seeds to us? Who's done random number generation? Nobody wants to step? Yeah? Was that a hand? Yeah? So how does random seeds work? Why do we have this random state thing?
What I gather, I think it's most seeds are based off clock time, and they randomly generate it's procedurally generated.
Yeah. So can I rebroadcast for the class and the Zoom, or not Zoom, podcast? So the idea is this. Random numbers in a computer are not actually random. Okay? There's no, I don't know, little subatomic particle vibrating randomly inside your computer to generate random numbers. It would be cool if there was. So all random numbers in a computer are what's called pseudo-random. It means they're actually algorithmic, okay? So it's a sequence. It starts somewhere, and then it goes through an algorithm, which is something like add 13, divide by 2, multiply by 12, okay? And when you run that sequence, whatever comes out of that algorithm is now where we go from the next time. So we draw out a random number, but we've got inside this number. And then we go through that same algorithm again, right? And the sequence of numbers it spits out looks random, okay? But it's not. If you start in the same place, you will get the same sequence. So when we set random state, which is something that we commonly have to do in machine learning, what we're saying is start your random number generator here, okay? Why this is good is replication, okay? Many algorithms in machine learning use random numbers. I publish some result in machine learning. I'm like, here, my algorithm is the best. And somebody takes my exact same code, but they start the random number generator in a different place, and they get a different answer. No longer is this algorithm the best. Now this other one is, because of random effects. So without a random state, there's no way to replicate an experiment. Okay? So knowing the starting value of a random number generator is super important for replication in machine learning work. Now, it still doesn't change the fact that you could still get a different answer if you change 42 to 173,209. Okay? But at least you know how the answer was generated. Okay, so we've got a training set and a test set. Let's fit our training set. And then, oh wait, I don't want to do all the y's. I want to just take, just for the simplistic sake, let's do pulse. Okay, we're just going to fit a single output variable instead of 3 output variables. Okay, so then we're going to predict with xtest. Okay, what'd I mess up? Train test split not defined. Oh yeah, it's important. From sklearn, model selection subunit, import train test split. All right, let's try again. Okay, so we got some predictions. How do they compare? Maybe we should save those predictions in something. So I'm going to call it ypred. And let's just really quickly make a data frame. So the y-trues are going to be y-test, right? Y-test was given to us by the splitter. They're the test set truths. And y-predict is going to be, all right, what'd I mess up? Somebody help me. Data must be one-dimensional. So what's coming out here? Sorry, I guess I should have done this in advance, huh? Oh, that's why. It's the y-test part. Dummy. Y-test, I was only fitting pulse. All right. So we can see the truth, we can see our predictions. Doesn't look like we did a good job. But, you know, so how can we measure that? We could measure error, right? If we're going to somehow, you know, figure out what is the best version of this model, we need a metric. So let's see if I can remember correctly. Is RSS okay? It's not built in. So okay, mean squared error is not exactly residual sum of squares, but it is related. It's the residual sum of squares divided by the number of data points, right? So how does that work? We pass it the true value, and then we pass it the predicted value as the second argument. So truth first, that's going to be y-test, and predicted second. And what did I screw up? Again with this. I'm not remembering ever. All right. So there's a number, right? And if we multiply that by the number of data points, it would be the residual sum of squares, which is our loss function in the beginning. Okay, so if we go back, we think about this, right? If we wanted to compare our models, we could compare that metric, right? And critically, I want to point out what we're doing down here. We are not computing this metric on the training set. We're computing it on the test set. Because again, the test set is, like it's going to be a different set of these blue dots. Okay? All right, does anybody have any questions? Okay. I highly suggest you play this game on your own. Get a notebook going, run, start with this one, load up a data set, you can explore the data sets, you can try predicting stuff. Right. In the meantime, let's do some slides. Okay, I do need to make a couple of quick announcements because there have been some common assignment problems. I just want everybody to be on the same page. I've encountered one person who didn't have Git installed on their computer, and they were trying to make the Conda environment. And the Conda environment creation requires Git. And what I was shocked to find out is that it didn't throw an error. It just silently did not install 2 packages that come from a GitHub repo. Okay? So just be aware, if you made a Conda environment using our YAML file in that Docker files repo, and you didn't have Git installed, oops, you should probably do that again. I have updated the YAML file to enforce Git before it does anything else. There's been some Markdown and general LaTeX issues with assignment 1. So I don't know why, but for whatever reason, after you set up a math LaTeX thing, list is not working for some people, like using bullet point lists or numbered lists. I don't know why, but apparently it's a thing. So maybe don't make numbered lists after you've used math, or don't use numbered lists at all for Markdown. I don't know what's going on. If anybody figures it out, put a bug report on CampusWire so if we know how and why it's happening or how to fix it. In general, inside Markdown LaTeX, if you're trying to do anything multi-line, you must use double $signs, okay? These kinds of $signs are just for like having a sentence where you're like, and when we optimize W inside strings, right? And then you go on with your sentence. But if you're trying to write an equation, or especially an equation that spans 2 or more lines, you need the double $. If you're using an aligned thing, it is /aligned, not /align. That's a different LaTeX environment that people are getting confused with. In general, if you want to debug your own LaTeX, then you should use from your browser, right, from the Jupyter Notebook, file export PDF via LaTeX, however you like to say it. And then you can see the generation that's going to happen when you upload it to Gradescope, okay? And you can do your own double checking and debugging. And lastly, all you people who are sitting there and going, ha, 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 I didn't use LaTeX at all for math. I just took photos on my phone and uploaded the photos. Well, there's a couple of bugs there too. Number one, do not upload your iPhone's HEIC file formats. That's so Apple. Nobody else knows what to do with that. Turn those into JPEGs or PNGs first. Otherwise, it doesn't work. Number two, there are some issues. Apparently, if you don't have the right autograder, that, if you didn't get the GitHub installed autograder, then the export wasn't taking your images with it. So just as an extra precaution to make sure A2 goes well, if you have already downloaded A2, just pull it again out of the repo. Also, if you're not absolutely sure that you have the right autograder, just take those lines that are in the top of A1, which does a pip uninstall of autograder, and then pip installs it immediately with the right stuff. Just copy that and paste it into A2 and do it. Okay. If you're confused, office hours, discussion section. All right. Sorry about all this. This is all teething. We're going to get this stuff working. Okay. This is the bias variance trade-off. You're going to get sick of me talking about the bias variance trade-off because it happens everywhere in machine learning. It happens like you blink and it's a bias variance trade-off. I'm sorry. So you're probably used to this kind of an image, right? A low bias distribution is one that is centered on the truth. This is the ideal situation because it has both low bias, the center of this mass is right where it should be, and low variance, the shots are all grouped tight together, right? This has got low bias too, okay? It's just that the spread, the variance around the shots, is quite a lot higher, but the mean is where it's supposed to be. These are both low bias situations, okay? These are high variance situations on the column here. And obviously, this is the worst case scenario where our mean is off and our variability is high, okay? Now, in machine learning, oh, come on, will you please unlock? In machine learning, the weird thing about it is that there is an explicit trade-off in almost every single thing, such that it is nearly impossible to get here, and it is nearly impossible to get here. Whoops, did I do that wrong? Wait. So this is low bias and low variance. This is high, sorry. That's what I was trying to X out. I'm dumb. All right. We're almost always in a situation where when we squish variance out, we induce bias. And when we squish bias out, we induce variance. So we're continually in a trade-off trying to figure out where in this continuum we want to be. As you look at me like I'm an idiot, because this doesn't make any sense, let me try to illustrate for you. So here's our two models that were extreme, right? That we said one of these is way underfit, one of these is way overfit. What is going down here? Well, it's the bias variance trade-off in action. Because there's random noise in those blue dots, right? The high bias situation with just fitting a constant, it is biased to see the world in super simple terms, just the mean of the y's, okay? By enforcing that bias, we are rejecting variability because another draw of this same random distribution, right? If I get, instead of these blue dots, I get these green dots, Well, their mean of their y's is going to be really, really close, okay? It's going to be like that, okay? So when I take another sample, the variability, whoops, I thought I had a better, I guess I didn't copy in my other slide, okay? So the variability here is going away because the simplifying assumption, the bias towards a super simple solution, is eliminating the variability. A different random sample is going to have pretty close to the same mean, okay? On the other hand, the different random sample here would have a radically different model, okay? The ninth order polynomial has got no bias towards simplicity. It's just going to fit exactly where those data points are, okay? So a different random draw is going to give radically different coefficients, okay? Does this make sense? So the bias variance trade-off here means that when we have a super complex model, we can overfit it, and a different random draw from the same process will get us radically different weights. But the simplifying bias towards a super simple model in the constant model is going to eliminate a lot of that variability. Make sense? Yeah.
Do we want each of these depending on the situation?
Yes. Yeah, there's no right answer here. This is a trade-off. And obviously, different kinds of data and different kinds of problems, the trade-off is going to look different, and what your needs or fears or things you most want to avoid are going to be potentially very, very different. Okay, so let's just kind of think the model selection thing. So when we want to find exactly the right version of our trade-off, when we're looking at model complexity and trying different models, I just want to keep in your head that here's some terminology. I'm going to try to enforce. Sometimes I use the terminology wrong. But obviously, the training set is how we're going to fit parameters, right? I'm going to try to always say validation set when what I mean is try 0th, 1st, 3rd, 6th, 7th, 9th. Calculate your errors on the validation set. Pick the model that gives you the lowest errors on the validation set, okay? So validation sets are for model selection. They're for validating a model. Yeah?
So if that would be like your original data pieces where you just validate on the things.
Yeah, so you generally don't want to validate on your training set. Correct. That's because that is an extra fun form of overfitting. We'll get to why that gets into it another time.
If you calculate the error for two sets and they have the exact same error, is there a way to know which one's
There are principles. How about this? Realistically, if this is an error value and this is a model, right? So I'm going to model 1, model 2. Okay. Realistically, you never actually just do this once. These are statistical things. So your performance level is going to be a mean plus or minus a standard deviation. Those two models don't have any distinguishing difference between them, whereas this model over here is definitely better, right? But if you don't have one of those situations where the error bars don't overlap, how could you choose between these two? One idea might be parsimony principle, might be Occam's razor. Which one of these two models is simpler? Okay? So that's one thing you can do. We'll talk about this a lot in week 5. Okay? But yes, the answer is yes, there are things to do even when they look the same. Okay. here you've got a validation set. Oh, sorry.
So just to go back to the previous slide, why can't the validation and the test set be the same?
Okay, that's a really good question. I should have finished that out. So it works like this, right? Once we have selected a model, right? We had 9 models. We chose our best one based on the validation set. Now we want an independent view of how good that model is. Because the same way we could have overfit to the training set, we can also pick our model based on overfitting to the validation set. So having a completely separate test set is an independent evaluation of how good this model actually is and how well we expect it to do next month when we get an entire new batch of data in. Does that make sense? So it is true that you can declare a winner based on random noise. And if you did a different validation set, you would get a different winner. It sucks, right? But the most important thing you can ever learn from this class is there should be no leaking information between these data sets. If you have like one data point that's in your training set and in your validation set, you have leaked information, right? There was a little bit of information, this one data point that was in both sets, and you have accidentally fit on this data point, and you've also used this data point to help pick your best model. And remember, machine learning algorithms are going to be way better at data they've already seen, right? So it's going to tend to bias your system to select the more complicated ninth order-like model, which is going to be able to perfectly fit that data point. That ninth order model is going to do frickin' great because it's already seen this data point. Yeah?
But then why can't we just use the test set to choose the model as well? Like when you test, you see which one has the lowest error. What's the problem with that?
So, once again, you are in a situation where you are fitting a model based on the validation set. You're picking your winner. Next week, you get a new data set with completely different noise pattern in it. Your overfit, your choice of winner was based upon data you've already seen. So you can, your estimate, so the point is that the test set is your estimate of how good we're going to do next month and next year on new data like this. And you're going to tend to overestimate how good you're going to be because validation set has selected your model. Yeah?
So the validation set and the test set never get placed into the training sets, or are they always kept separate?
So it depends on your setup. There's some weird caveats to this, right? So there's ways to be very, very efficient with your data. We'll talk in week 5 or 6 about nested cross-validation. And in nested cross-validation, every data point takes a turn at each one of these jobs, okay? So it's wacky, but I'm not trying to tell you this never happens, but in general, you want to keep these completely separate, okay? If in doubt, keep them separate. If you've got enough data, if you have like an internet-sized data set, absolutely you're going to keep them 100% separate. You only need to reuse data when you only have like a couple of hundred data points and you're trying to make the best of the bad situation. Okay, so we're going to talk a lot more about this stuff over time. But let me introduce to you a validation curve. And I generated this with a scikit-learn call that you should explore yourself called validation curve. Okay? It's lovely. How does this work? Well, we can see here the error on the training set and the separate validation set in the same curve. And that helps us diagnose what's going on. So what's going on? Let me remove this. This direction is more complex. Okay? More simple over here. in terms of models, right? 0th order models on the left, 9th order model over on the right. We know from the 9th order model picture that we're going to be able to absolutely hit every single one of these points. So at that point, our training error is 0. Right? The blue line is training error. We've gone to 0. We've perfectly fit. Basically, when you see training set error of 0, you know you're overfit, right? Unless it is the simplest possible problem in the world, you know you're overfit at training set error 0. Okay. So in the underfitting regime, what we're seeing is that validation set error is going down roughly with the training error. We haven't yet bottomed out, right? We haven't gotten to an optimal model performance. When we start to overfit, the training set error keeps going down, but the validation set error starts to go back up because we've learned the noise in the data. And so when we get a new sample in for validation, we don't do so hot, right? So this diverging zone shows you when you're overfitting. And this following each other zone is when we're still underfitting, where our model complexity ain't enough yet, because we're still getting better as we add more parameters to our model. Okay? So this zone in here, this is like your question. This is all pretty much the same result, right? They're all doing about as well as each other. So of these models, which one should we prefer? Well, Occam's razor says, given two explanations that are just as good at explaining the phenomena, pick the simplest one, right? Thank you, monk from 1500 something or whatever, right? So, okay, so the simplest model is the 3rd order model, right? It's simpler than the 5th order model over here. So you might just say, okay, that's me. That's my model for this setup. Questions? Worries? I don't even know what time it is. How are we doing? 47, okay. So we're getting to the end here. All right. So let me now introduce to you, in 3 minutes, the idea of regularization. We'll come back to this. So you have seen this now more than once. This is ordinary least squares. The idea of regularization is an easy one. The idea is that when your weights get too big, your model is too complex, okay? The big weight values, especially like, for instance, in a polynomial regression, if the weight values are large in the 8th order, right, x to the 8th, that's a pretty complicated model. So how could we prevent overfitting if we're using an 8th order model? Okay, I don't want to change my model. I just want to keep a complicated model. How could I prevent it? Well, I could keep the 8th order or any order weight values small. I could try to penalize large weight values. How could I penalize large weight values? I could use an L2 norm or an L1 norm to measure the magnitude of the weight vector. And I can add a penalty term to my loss function, which just says, hey, not only do I want you to, minimize the residual sum of squares, right? I'm minimizing that. That's my loss function. I also want you to minimize the magnitude of the W vector. Squish it. Squishing the weight vector prevents overfitting. Okay? This is regularization, squishing the weight vector conceptually. Mathematically, you're going to use some norm, L2, is called ridge regression. If you use L1, it's called the lasso. That's an acronym. I'm not going to remember the acronym. And we will talk more about this next time. Hey.
So, kind of screwed up yesterday, and I forgot to submit the Lecture 5 lecture quiz.
Okay.
Is there any chance I can do that for my credit now?
No. So if you look in the syllabus, we drop 4,
Okay.
I think. So you're pretty safe.
Okay.
And it's just too much work. So.
Okay, I got you.
Yeah.
Also, I was thinking about this a little bit. You're really the only professor that I've had that's